Hello, everyone, and welcome to today's presentation. I'm excited to talk with you about supervisory control and data acquisition, or SCADA, systems. Our focus will be on how these sophisticated cyberphysical tools are vital for the effective monitoring and control of water resource recovery facilities. We'll explore how SCADA systems act as the critical link between operators and instrumentation, collecting data from the field and helping us maintain smooth facility operation. Think of them as the brain that processes information from sensors and aids us in making informed decisions. So, let's dive in and see how SCADA systems keep our water facilities running efficiently and reliably. Let's begin by understanding some common operational problems with SCADA systems. These can include issues like faulty sensors, communication failures, or software glitches that can disrupt the entire process. Recognizing these problems is crucial because they directly impact the reliability of the data we rely on. Speaking of data, it's vital to understand the critical value of the information collected by SCADA. Accurate data is the backbone of effective decision-making and control. If the data is unreliable or incorrect, it can lead to improper operations, which might cause process inefficiencies or even safety concerns. Now, moving on to monitoring and control applications, these are the core functions of SCADA. They allow us to observe system conditions in real time and make adjustments as needed, whether remotely or locally. This capability enhances operational flexibility and responsiveness. Next, let's identify the major components of a SCADA system. These include control panels, which house the control equipment, I/O devices, which connect sensors and actuators, controllers that process data and execute commands, networks that facilitate communication, and operator interfaces, which display data and allow user interaction. Understanding how data flows through the SCADA architecture is also essential. Data originates from sensors and devices, travels through communication networks to controllers, and then is displayed on operator interfaces. This seamless flow ensures timely and accurate information for decision-making. Finally, appreciating the importance of SCADA systems to facility operation is key. They serve as the nervous system of a facility, providing situational awareness, enabling remote control, and ensuring smooth, safe, and efficient operations. Without reliable SCADA systems, managing complex processes becomes significantly more challenging. Remember, as cyberphysical systems, SCADA can directly influence equipment operation, like adjusting valves, starting mixers, or changing process parameters. But this all depends on the foundation of accurate instrumentation. If the input data is flawed, the entire system suffers from what we call garbage in, garbage out, meaning poor decisions based on unreliable data. Overall, SCADA systems are vital for providing real-time situational awareness and collecting data that supports operational decisions throughout the utility. They act as the central nervous system, translating complex process information into understandable formats, so operators can effectively control and optimize facility performance. In this architecture, information flows bidirectionally, meaning data moves both upward and downward through the system. Field data, which includes measurements from sensors and other input devices, travels upward to operators for monitoring and analysis. At the same time, commands and control signals flow downward from operators or control systems to the equipment, enabling real-time process adjustments. This continuous feedback loop is crucial for effective process control and optimization. Moving on, we have the human-machine interfaces, or HMIs, which are the visual dashboards operators use. These interfaces display real-time process information, allowing operators to monitor conditions, adjust set points, and issue commands seamlessly. The HMI setup typically includes workstations, servers, and historians, all working together to collect, store, and analyze data to support decision-making. Next, let's look at Level 5, the operator interface. This level encompasses the communication infrastructure that connects controllers to each other and to the operator interfaces. It can include wired connections like copper or fiber optic cables, as well as wireless solutions. Often, Ethernet and Internet Protocol technology are used here, providing reliable and flexible communication paths. At level 4, we find the networking layer, where programmable devices such as PLCs, RTUs, and DCUs come into play. These devices convert raw I/O signals into standardized units, assign tag names for easy identification, perform calculations, and execute automatic control sequences. Essentially, controllers at this level keep the process parameters within the setpoints defined by operators. Moving down to level 3, we encounter the controllers themselves, modular circuit boards that receive analog and digital signals from the field devices. They convert these electrical signals into data that computers can interpret. Each signal corresponds to an I/O point, with common inputs including 420 mA analog signals and 24-volt digital signals. At level 2, we have the I/O devices, sensors and instrumentation that directly contact physical equipment. They provide signals about the process conditions, including digital signals like on-off statuses, and analog signals that vary continuously, such as pressure or flow measurements. Finally, at level 1, we see the field devices themselves, those sensors and instrumentation directly touching the physical process. They are the foundational layer, providing the real-time data that fuels the entire control architecture. Understanding how these levels connect helps us see the full picture of SCADA system operation and control. Let's take a closer look at the industry's standard 420 mA current loop. One of its key advantages is the concept of a live zero. At 4 mA, this means that even when the sensor isn't providing any measurement, the current remains at 4 mA, allowing SCADA systems to detect if there's a failure or broken wiring if the current drops all the way down to 0 mA to ensure the signal stays accurate and free from interference. We use special twisted pair cabling with electrical noise shielding. This setup is especially important in industrial environments where electromagnetic interference can be a real challenge. Now, moving on to analog signals, they vary continuously within a range of values. For example, pressure sensors installed on pump discharge piping give us signals directly related to the gauge pressure. These signals can range from 0 up to a maximum pressure, providing real-time, precise measurements. These sensors are paired with transmitters that convert the raw pressure readings into reliable signals suitable for long-distance transmission. Switching gears to digital signals, they represent binary states, so there are only 2 possible values. Think of electrical contacts on pump motor starters. When the motor is off, the contacts are open. When the motor runs, they close. These simple on-off switches give us clear, unambiguous status information, which is easily interpreted by the SCADA system. Finally, understanding the different signal types and how we transmit them is essential. Analog signals offer continuous data, while digital signals provide discrete states. The choice of transmission technology depends on the specific application, environmental conditions, and the need for accuracy and reliability in the system. All these components work together to ensure our industrial processes are monitored and controlled effectively. On this slide, I want to emphasize the importance of security when working with SCADA systems. First, never connect unauthorized devices, such as visitor laptops, directly to the Ethernet switches that support SCADA. Doing so can risk spreading computer viruses and compromising system integrity. It's crucial that only qualified staff have access to the control panel interiors, especially since these panels often have multiple power sources that need careful handling. Moving on, the Ethernet switches and communication devices are vital for enabling controller-to-system communication. While these devices are based on standard Internet protocols, they are isolated from the Internet to enhance security. This setup helps prevent external threats from reaching the core control systems. For physical connections, we typically use copper cables with clear connectors or fiber optics, which provide noise immunity and support long-distance runs. The LEDs on these devices are useful diagnostic tools. They show connections' status and activity, helping us quickly identify any issues. Now let's talk about the network equipment itself. Industrial computers handle the core SCADA functions. Often, these computers are installed in the same chassis as I/O cards and share the same power supply, which simplifies the setup. For critical processes, we use redundant controllers so that if one fails, another can take over automatically, ensuring continuous operation. The diagnostic LEDs on these computers give us immediate visual feedback on power, programming, faults, and communication health. Next are the controllers, or PLCs. These are circuit boards grouped into chassis, known as I/O racks, which connect directly to field signals. They include various types of cards, analog inputs for signals like 420 MA or 15 VDC, digital inputs for 24 VDC or 120 VAC signals, and outputs for controlling devices through relays or solid-state components. The LEDs on these controllers provide first-level troubleshooting, helping us quickly identify issues. Finally, the input-output devices are housed in safety cabinets. These contain the controllers, I/O modules, power distribution equipment like circuit breakers and fuses, and wiring terminals. On the door-mounted components, you'll often find power disconnects, control switches, pilot lights, and interfaces for local operators. All these elements work together to create a reliable and secure SCADA system that supports the entire industrial process. Let's take a closer look at how different components work together in a SCADA system. First, we have the historian servers, which are responsible for collecting and storing process data from the SCADA servers. This stored data is essential for creating trending displays, generating reports, and sharing information with other business systems. By doing this, we enable long-term data analysis and ensure regulatory compliance. Next, the SCADA workstations play a vital role in presenting this information visually. They display graphical views of the process, alarms, and animations, making it easier for operators to understand what's happening. Operators can adjust setpoints and send commands through these workstations, which communicate with the controllers via servers. These computers are equipped with excellent video capabilities to support direct operator interaction. Moving on, SCADA servers are the backbone of communication within the system. They connect with controllers, provide process data, and handle alarms for other HMI components. These servers are high-end, reliable computers designed to serve as the central hub for information and ensure smooth operation. In larger facilities, HMI functions are distributed across specialized computers to improve efficiency and reliability. This setup allows for dedicated control rooms that handle critical SCADA functions, such as controller communication, alarm management, graphical displays, command execution, and historical data collection. The human-machine interface, or HMI, is typically mounted on control panel fronts. These local operator interfaces, or LOIs, give operators quick access to process views close to where the equipment is located. They're invaluable during maintenance and troubleshooting, providing convenient monitoring options. Additionally, LOIs serve as backup control points if the facility-wide SCADA communication system experiences issues. Sometimes, they may include vendor-specific displays for detailed local process information, especially in packaged equipment systems. Overall, these components work together seamlessly to ensure continuous monitoring, control, and data management across the facility, supporting safe and efficient operations. Let's talk about moving between displays of the same level. This is crucial for optimized navigation because it allows us to quickly switch from, say, process X to process Z without having to go back and traverse the entire hierarchy. It's a seamless way to jump around efficiently and works hand-in-hand with drill-down methods for smooth operation. Now, starting at a high level, we have lateral navigation. Imagine beginning with an overview of the entire facility, then drilling down step by step, first to specific locations, then to particular processes, and finally reaching device faceplates. For example, you might start at the facility main, move to the wet side, then to a specific process, and finally access device controls directly. Speaking of drill down, this is all about methods to open relevant pop-ups, whether for general information or controls, and faceplates, which are device-specific control screens. These pop-ups and faceplates give us quick access to the detailed information or controls we need to operate safely and efficiently. Each display should have a clear title that accurately describes the process shown, along with comprehensive data visualization. This clarity helps operators easily understand what's happening and ensures safe operation. In addition, navigation areas include pull-down menus, arrows, and frequently used display buttons, providing quick access to other screens or functions. This makes switching between displays intuitive and reduces the chance of getting lost in the system. Finally, standardized display regions are key. Consistent layout, colors, graphical elements, fonts, and line weights help organize information logically. We also maintain consistent color schemes for statuses, like running or stopped, and alarms. This consistency minimizes operator confusion and enhances situational awareness, especially when identifying abnormal events quickly. All these strategies, lateral movement, drill down, clear titles, intuitive navigation, and standardization, work together to create a coherent and efficient operator interface, supporting safe and effective process management. Now, let's talk about alarm acknowledgement. When operators see alarms, they indicate they've acknowledged or are actively resolving them. Acknowledged alarms are those we've already recognized, while unacknowledged alarms are new alerts that still need attention. To help us quickly identify their importance, these alarms display differently. Both are color-coded by priority, with the highest priority alarms appearing at the top for immediate focus. Speaking of priorities, response times vary depending on how critical the alarm is. For low-priority alarms, a timely response is expected, but they don't require immediate action. Medium-priority alarms need urgent attention, so we should respond quickly. High-priority alarms demand immediate response to prevent escalation, and critical alarms are the most serious, requiring instant action. It's important to remember that not all alarms are equally critical. For example, responding to a chemical spill alarm differs vastly from responding to a motor vibration alert. To manage this effectively, we typically categorize alarms into 4 priority tiers, each with documented minimum response times to ensure timely handling. Moving on to the alarm management system status. If a device is out of service, it means it's unavailable for operation, which could indicate a power issue or other technical problems. Conversely, when a device is in service, it's available for operation, though the exact definition can vary depending on the system. Sometimes it's just within the SCADA system, other times linked to physical power. Now let's discuss control modes, starting with service modes. Equipment can operate in auto mode, where controls are managed programmatically by PLCs, DCUs, or local controllers. This can range from simple pump sequencing based on levels to complex PID loops maintaining process variables at set points. Manual mode, on the other hand, involves operators explicitly controlling all functions, which may include some interlocks for alarms that shut off equipment when necessary. We also have auto-manual control options. Auto control is typically used when equipment is managed remotely via SCADA, especially useful during communication losses or maintenance. Local control means the operator physically operates the equipment from a nearby location, often requiring a physical visit to change modes. Understanding these control modes and alarm management strategies helps us maintain safe, efficient, and responsive operations across the facility. Now, let's talk about the importance of qualified staff performing software updates. This ensures both functionality and security are maintained at the highest standards. As you listen, pay attention to any changes in fan noise, which can be an early indicator of equipment issues. Regular cleaning of screens, keyboards, and mice is also essential to keep systems running smoothly and to prevent any potential malfunctions. Periodic operation testing is another key point. By regularly testing the system, we can confirm that everything is functioning correctly and catch problems early. When it comes to operator interface care, it's important to note that only qualified staff should inspect control panel interiors, especially since there are multiple power sources involved, which can be hazardous for untrained personnel. If you suspect any issues, creating work orders is the best way to ensure problems are addressed promptly. Also, always look for signs of insects or rodents near the panels, as these can cause damage or short circuits. Confirm that front-mounted equipment is functioning properly and listen for any fan noise changes that might indicate failure. You should also verify that no liquid is dripping on or from the panel, which could lead to electrical faults. Make sure doors are properly closed to maintain safety and environmental protection. When inspecting control panels, these routine maintenance steps help prevent unexpected failures and keep the system reliable. Moving on to data collection and reporting, SCADA systems are vital because they gather and store operational data with timestamps. This data is crucial for trending and reporting, especially for flows, levels, and chemical analysis. Since operational decisions and regulatory reports depend on this data, its availability and accuracy require constant attention. Regular review of trend displays ensures the system is operating correctly and that data collection is accurate. The data supports real-time decision-making, monthly regulatory reporting, maintenance work orders, and engineering analysis. This interconnectedness highlights why consistent data management is so important. Now, regarding trending methods, there are three main types. First, ad hoc trending, which allows operators to quickly view trends of specific data points on demand, providing flexibility without needing a technician. Next, pre-configured trends are embedded directly into displays, enabling real-time visualization of critical process values, helping operators catch issues before they escalate. Lastly, embedded trending involves simple to complex graphs that monitor process values over time, such as flow rates or water levels, tailored to different operational needs. Together, these trending capabilities empower operators to maintain optimal system performance, troubleshoot effectively, and support overall plant efficiency. Remember, SCADA systems are cyberphysical systems used across many industries beyond wastewater treatment. They rely heavily on instrumentation, which forms the foundation of the system. If the input data is unreliable or inaccurate, the entire process control can suffer. That saying, "garbage in, garbage out," really applies here. If your data is flawed, so is your decision-making and control. System integrators play a crucial role by bringing together equipment and software from different vendors to create fully functional systems. Because of this, the terminology for components might vary from one facility to another, so it's important to understand the specific setup at your site. Always verify that the displayed data makes logical sense. For example, if the inflow to a tank remains constant while the outflow increases, the tank level should gradually decrease over time. If it doesn't, that discrepancy could point to SCADA or instrumentation issues that need investigation. Continuously perform reasonability checks. Check the diagnostic graphical displays that show alarms for individual equipment. These screens provide detailed information about the health of each component, helping you quickly identify potential problems. Review the diagnostic displays regularly. Confirm that SCADA is properly collecting, storing, and displaying data. Look out for data gaps that indicate collection failures or flat trend lines where variation is expected, which could mean signals aren't updating. Excessive variability might suggest electrical noise or instrument problems, while oscillations could indicate tuning issues with PID loops or maintenance needs. Frequent monitoring of trend displays is essential. Doing so helps catch developing issues early before they escalate into bigger problems. Make reviewing alarm logs and summaries a routine part of your process. Regular checks allow you to identify and address issues proactively. Remember, SCADA systems are tools to assist operators. They don't replace the operator's awareness. Maintaining a strong overall process awareness and performing reasonability checks are critical. These practices enable you to recognize system issues quickly and respond effectively, ensuring smooth and reliable operation.